This talk will be quite different from my last talk at Rust Linz. That talk was quite general and about why you should care about Rust. This is a much more technical talk, but don't worry, it's still hopefully going to be very approachable and open for everybody. We're going to be talking today about Rust before main, as in Rust, what happens to a Rust program before you ever reach the main function. But before we begin, a little bit more about myself. I'm Ryan. I work at Microsoft as a developer advocate for Rust. I'm also on the Rust core team, on the Rust Foundation as a project director. So my life is very much consumed by Rust. I got into programming a long time ago, kind of on accident through my job, where I learned that I really liked this stuff. And as I've gone along through my career, I've kind of learned more and more and gone deeper and deeper in the stack. About 2 years ago, I kind of ended up learning about what happens to a program to get it to execute, which I didn't even realize was a question I had. So let's talk a little bit more about that today. So the journey that we're going to be taking together is to answer a couple of questions. The first question is, what happens actually when we run a Rust binary? What's happening in the computer? What's happening in the operating system? How do we actually get to our main function? What even is a Rust executable? What does that even mean? The answer might surprise you. What tools can we use to inspect Rust executables so that we can look into them? And just so you know, everything we're going to be talking about today is only going to have to do with Linux. But don't worry, if you're a Mac OS or Windows user, this stuff will sort of kind of translate. A lot of the concepts are very similar on those platforms, but they may not be quite the same. All right, so let's talk about my mental model before I learned about all this stuff, about how a binary executable actually runs. So here on the left, we have a binary. And most people know that a binary is binary. It's a whole bunch of ones and zeros. And I imagine that when you executed a binary executable, you just started at the very beginning of the file and you interpreted whatever those ones and zeros were as assembly instructions for the given architecture that you're on. Let's say at the beginning here, we have a load B into A instruction here. And then we go to the next one after that, and it can move around. We can have a jump here, for instance, so we can jump to another place in the binary, and then we execute again. And that's kind of how executing machine code or binary code works in practice. And this isn't necessarily wrong. It's just a little bit too simple. So if this is your mental model, it's fine. You can keep it, but just know that you're not seeing the full picture when you think of things this way. And we'll explore a little bit more around this. So before we get started, a few tips on how to think about things, how to approach these problems. First of all, it bears to be repeated, computers are not magic. There's nothing necessarily magical happening here. It's really all just kind of engineering at the end of the day. That means all of this is ultimately understandable. It may not be obvious at first, and you may not get it without kind of putting a lot of effort into understanding it, but it is understandable. It's not magic. It's not something that you have to divine from the stars. It's all there for you to understand. Everything you see here was made by humans. It is a deliberate choice. It didn't have to be this way. It just ended up being this way. Some of that is because of deliberate engineering choice, and some of those choices you could argue were good choices. And some of it is just kind of random circumstance. An engineer working on something kind of had to make a decision, and they said, well, given a couple of choices, I guess we'll go with this one. There weren't really any good reasons for that decision, but they made it, and now 40 years or 50 years later, we're kind of stuck with it. So don't just assume that if you see something that's funny or it doesn't look quite right, it's because you don't understand it or you're not smart enough. It might simply be because it's kind of just random. At any given point, it's not always easy to tell which between deliberate choice and random circumstance a given decision might be. And unfortunately, out there in the world, some explanations are not always the best. So just because you don't understand something doesn't mean that you're not smart enough. It might be that the person just doesn't want to explain it very well. So don't give up. Before we begin, I'd like to talk through the Rust compilation model. And this is vastly simplified and in some ways not even fully correct, but it's important for this talk that we kind of understand how Rust compiles code. So you have some code. Here's a main function printing a wave emoji here. And we're going to pass that Rust code over to rustc and LLVM. And of course, most Rust users usually use cargo, but hopefully everybody here knows that cargo is the build tool, and ultimately what cargo does is call rustc, the Rust compiler. And rustc is a front end that can interpret, parse, and understand Rust code, and LLVM is the back end that rustc plugs into that takes rustc's understanding of your code and turns it into machine code. But what it does, what LLVM ultimately produces, is object files. And these are kind of groups of functions, metadata, and things about your program in separate files, depending on what the particular compilation unit is. Typically, this is at the crate level in Rust. We get those object files. These are not really executable quite yet. They have to be linked together. So we take those object files, we add in a linker, that's LD in the case of Linux often, and out from the linker comes a binary executable or a binary library, a shared library of some sort or something like that. And that is a program that can actually be run. So that's the compilation model. Keep that in mind. That's what happens before we even start to run our program. So what is the program that we're going to use today? It's going to be a very, very simple one. This is it. It's a main function, and all it does is call std process exit with the exit code 0. This simply exits and makes the exit code the number 0, signaling typically success. There's an issue with this program, though, for our purposes. When we compile it and we look at it, even in release mode, it turns out that it's 3.8 megabytes big. That's a little big. Probably too big for our purposes because it kind of makes things difficult to look at and inspect when you're dealing with a whole bunch of stuff. It would be much nicer if we could still have the same Rust program, but a lot smaller. We can do that pretty easily if we go into our cargo.toml file, and under the profile.release section, we put in a couple of nice features that we have here. The first one is strip, that can strip out some unnecessary things in your binary, because your binary includes things like debug information, which, if you're not debugging your program, you don't really need. And some other symbols and things like that can help with tooling, but are not necessary for the actual running of the program. The next one is opt level, optimization level. We set it to Z, which optimizes for size instead of for speed. Doesn't really matter for our program because our program doesn't really do anything anyway. So this shouldn't really make a difference other than make it smaller. LTO is turned to true. That's link time optimization. That gives the linker additional ways to optimize the size of our program. And the last one is panic abort. And if you're not familiar with this, this is simply changing the way that panics work in Rust from unwinding the stack, giving you a nice message with the stack trace and things like that, to simply aborting your program, stopping the program cold. And it turns out that we end up with a program that's 93% smaller if we just add these 4 options here. So that's easy. But 268 kilobytes is still pretty big. And it turns out if you compile a C program that's of similar complexity, you're probably looking at around 15 kilobytes. So can we do any better? And it turns out we can by getting rid of the standard library. So we're statically linking the standard library. We're bringing it in. We're bringing a whole bunch of stuff that we don't actually need because we're not really using the standard library other than to exit. So this program here is even simpler. It actually adds an external dependency libc here, but that simplifies our program by allowing us to only use what we need. We actually define a real main function, not the Rust-specific main function. You have things like no mangle here. You can see no std, no main up there. So there is no main function. We're actually defining a main function ourselves. And we have to define a panic handler as well. What happens if this program panics? Well, we'll just go into an infinite loop. And if we do that, our program is much smaller. It's now 97% smaller than our original program at 14 kilobytes, which is roughly the size of what you would get if you did the same thing with C. So we're in the area. We didn't have to do a ton of work to get there. All right, 14K, much easier to work with. Let's start exploring. But wait, what is a binary executable? So we still don't know. We know it's ones and zeros, but like what shape are those ones and zeros in? And here we're going to use our first tool called hexdump, HD. And we're going to look at our hello world binary and look at the first line. And the clue to what this binary executable is in the very first line of binary code there. And you'll see ELF. Keep that in mind. We can also use the file tool to look. And the file tool is a nice tool that says, okay, give it a file. I'll try and find out to the best of my ability what I think this file is. And the file tool correctly sees that this is an ELF-Executable, 64-bit. And there's a whole bunch of stuff in here that you don't understand yet that you'll understand a lot better at the end of this talk. So we see this is an ELF file, an ELF file. Okay, that's good. What is ELF, though? Well, ELF stands for an executable and linkable format. So that is in the name, kind of describes what it does. It's a format of a file that is executable and linkable. ELF has information both for static linking. That's when we had the object files before, and object files are ELF in the ELF format, and they can be linked together. But it also has information for runtime execution. So our executable that we're actually going to run also is ELF, and the ELF file has information needed to execute that file. ELF is a database that allows us to look up the info we need to run our program. So we can almost query for the information that we need in order to run this thing. Well, it's not really us that's querying for it. It's more the operating system and another program we'll talk about later. The .text section contains our code. So there are different sections in this executable format. We're not going to look into ELF very deeply today. If you're interested, I have resources at the end. But there are sections in this format that kind of divide up the file format. And one of them is .text, and that contains our code. Why it's called text, I don't know. That's kind of a historical incident. Fun fact, though, the common debug data format on Linux is known as dwarf, and that's a play on the fact that ELF and dwarf are related to each other. Okay, so where is our code, though? Well, we're going to use another tool, object dump or objdump, and pass our binary to it with the -d flag on it. And -d allows us to disassemble the text inside of or the code inside of our binary. And you'll see here, we have our main function. It's right there. We see it, we're good to go. All right. But unfortunately, it's not the whole truth. So there's a lot more code here than just our main function. That main function is what we wrote. That's exactly it. It has XOR EAX. That is essentially making EAX register into 0. If you don't know assembly, that's totally fine. Don't worry about it. And then it returns. So it's doing very simple things, but there's a bunch of code around it, and we see interesting things in here that we probably don't recognize. We'll talk a little bit more about that as well. The .text section contains more than our main function, and there are even other sections that contain additional code. So this is just the text section, but there are other sections that contain even more code. So what is this other code? Well, it turns out main is not the entry point for our program. So we've defined main, and we're used to thinking main is where our program starts, but that's actually not true. It's usually the _start symbol is the real entry point for our program. So you can see here in our executable, we've run object dump with the -d to disassemble, and this is our _start symbol here. And again, it's a bunch of assembly. You don't have to worry about what it does. You can just breathe in the non-web assembly here, and we'll talk about what it does on the next page. Okay, so what is it doing here? Well, it's not that interesting. It's setting up the stack. So if you know about the stack versus the heap, there's a couple of instructions you have to do to kind of make the processor happy with your stack. It's moving argc and argv. Those are the arguments that you usually get in main function, typically in C, for instance. Those are command line arguments that you're getting in. argc is the count of them. argv is the actual pointer to them. So it's moving that to the right place. And it's basically prepping the call to libc start main. So you can see third line up there in the assembly, there's a call queue there. And that's call queue is just assembly for call a function. And the function that it's calling is this very weird and ugly named underscore underscore libc underscore start underscore main at glibc225. If you've ever heard of libc before, that's where that is defined. This is the function, the sort of main function for libc. So let's talk about that. The other main, libc start main. What does it do? It performs initialization of the execution environment. It calls the main function we provided with appropriate arguments, and it handles the return from main. And it does some other stuff, but we won't talk about that today. The function also calls various hooks that allow the user to change startup and exit. So you can actually define things in your binary that run before your program runs and after your program exits. There's a way to do this in Rust, but it's not quite so easy. And there haven't really been, as far as I'm aware, any kind of stable ways to do this in Rust quite yet. But you can hack the linker to do it. A word on dependencies. We're talking about libc here. We're talking about libc main and stuff like that. But like, where are these dependencies? Is libc like in our binary? No, it's not. So libc exists on your machine somewhere. And in this case, it's in /lib/x8664 Linux GNU /libc.so.6 is where libc actually lives. So it's in your on your machine somewhere, and our program is merely referencing to it, calling out to it. So this is what is called a dynamically linked dependency. It's not statically linked. It's not in our binary. It's living somewhere else. And we're using another tool here, LDD. And what LDD does is tell us what these dynamic dependencies of our program are. And it's important to remember dynamic versus static here. Most cargo dependencies and things like that are statically linked. They're brought into your program and live in your program. So if you're depending on regex or something like that from crates.io, it's literally inside of your executable. Whereas there are other dependencies that live separately. Like I said, LDD can show us binaries dynamic dependencies, and we're relying on libc.so.6. By the way, SO stands for shared object. This is just a term they use in Linux for libraries that are shared across the system. On Windows, you might refer to them as DLLs. So Linux VSDO is the first one there. And this is not super interesting for our purposes. It's basically provided there to kind of cache system calls so that they can be faster. The kernel kind of automatically maps that for us into our program, or it gives access to it for our program. And we've touched on libc, and we'll also touch on LD Linux x8664.so.2 soon. That's a very important dynamic dependency that we have. So stay tuned. Okay, so let's back up. How did we get here? So we're all trying to figure out how we got to main. Well, we start at _start, right? That's where we start. And then _start ends up calling glibc's _lib libc _start _main. And that function then ends up calling our main function. So far, that's how we get to main. We go from our start symbol into libc's lib _start main, and then finally to our main function. So does this mean that we can just call _start ourselves? And yeah, in fact, we can define _start ourselves as well. So before we were defining main, this time we're defining _start instead. And this works all fine, except if you try and compile this, you'll get a compiler error. And it will say, hey, you have 2 _start symbols here. You should only have 1. And that's because by default, the linker puts in an _start for you. So we have to, when we're compiling this program, tell the linker with this -c link arg thing here, hey, don't do that for us. And that's what no start files does. It just basically says, I'm gonna take care of starting, so you don't have to worry about it. And if we do this, it compiles just fine. So that's how we get from start. We don't even have a main function anymore at all, and we aren't even depending on libc anymore. This is kind of the purest Rust program that can run on Linux. But wait, why do we start at start though? Is there something special about _start that the kernel knows about or something like that? Well, turns out, no, that's not the case. This time we're going to use another tool. This is called readelf. And what read ELF does is allow us to read ELF and print it out in a nice format so that we can understand it. We're passing dash H here. And what dash H does is give us the header of our ELF file. And the header is a whole bunch of metadata. And the particular piece of metadata that we're interested in is this entry point address. This entry point address is what tells the world where we want to start executing. Where in this ELF file should the kernel or whoever start executing this program? And if we look inside of our ELF file at that offset that it was 1040 hex, you'll see it's at our start symbol. So the fact that it's called _start is more of a convention than anything. It's really, and it's a convention that the linker takes, advantage of and stuff like that. But from the operating system's perspective, it doesn't know anything about start. And in fact, _start is not even really there. It's just a label. It knows about that because of that metadata information inside of the header. All right. Then that begs the question, okay, then what calls start? Is it the kernel that calls start? And sometimes yes. Sometimes the answer is yes. But we need something in addition to just getting started. We need a couple of more services to be done for us. We need something that parses this ELF binary and maps it into memory for us. So we have a whole bunch of code. It exists on disk, right? But we need it in RAM somewhere so that we can run it, so that it's, and we presumably need to make it executable, because if you know anything about security when it comes to kernels, not all memory is treated the same. Some memory is readable and writable. Some of it is executable. We need to make sure that everything lives in its right place. How do we get the ELF binary from disk into memory? And then second, how do we load these dynamic dependencies that we have and put them in memory? How do we make sure that they're in our address space? Because they exist somewhere on disk too. So we need something that loads them as well. And we also need a way to ensure that our binary code can call them. So if somebody loads it into memory and our code is there, what address do we call to call into libc? Who does that mapping for us and things like that? Well, it turns out we need a tool called a dynamic loader. And this dynamic loader is also known as a dynamic linker, confusingly. And this is different than a linker, aka a static linker. This is a dynamic linker. And it's also known as a dynamic interpreter. So if you see any of these three names, you know that you're talking about the same thing. Dynamic loader, dynamic linker, dynamic interpreter are all the same thing. And what they do is essentially what we've talked about. Take this ELF binary, map it into memory, load dynamic dependencies, and ensure our binary can call them. The kernel does some of that stuff, and where the kernel starts and where the dynamic interpreter starts is kind of not for today. But we can think of the dynamic interpreter as doing a lot of this heavy lifting for us. So where is this dynamic linker? How does, who's running it, whatever? Well, it turns out our ELF file actually says what dynamic linker it needs to run with. And if we run read ELF and look at the .interp section, which is what -x.interp does for us, then it will show us here that it needs this /lib64/ld Linux x86 64.so.2 dependency. And if you remember back to LDD before, this is exactly the third dependency that we talked about that our binary has. So it was the kernel that put some of our executable into memory, and then it looked inside of our binary and said, oh, this thing needs a dynamic loader. Which one does it need? Oh, it needs that one. I'll load that one for it, and then I'll hand it off to the dynamic loader, and I'm out. So really, the kernel has a pretty simple job when it comes to things, and it hands off to the dynamic loader to do the really heavy lifting. Okay, so how do we get here? So we have a dynamic loader that the kernel hands the dynamic loader this executable. The dynamic loader does a whole bunch of work that we're not even going to get into today because unfortunately we don't have enough time. It does things like map memory. So it takes the stuff that's on disk and puts it into the right place in memory. It loads our dynamic dependencies. It does something called relocations, which is a whole nother subject, essentially saying you want to call this function over here. Well, where in memory is it? Okay, I'll basically hot patch your program to be able to call that that function in the right place in memory. So if you thought of binary executables as being very static things, I hate to break it to you, there's a whole lot of dynamicness to static binaries. And then eventually, when the dynamic loader is done with everything that it needs to do, it jumps to _start for us. And that's when our program takes over. Okay, so we know how we get to we know how to get from the dynamic loader to the _start symbol, and we know how to get from _start to main. So like we're almost there, right? Where at some point we have to stop this madness, and we have to just be at the beginning, right? So what actually invokes the dynamic loader? And that is this XCVE call. And this is the system call that Linux provides for actually executing a binary. And as we see here, XCVE executes a program referred to by the path that's passed to it. This path must be either a binary executable or a script starting with hash bang interpreter. So, you know, if you've seen that in a script before, then you know where that comes from. If you want to run Ruby or Python or something, that's where that comes from. And basically then that loads it into the kernel, and the kernel looks at the ELF-Executable, looks at the interpreter named in that .interp segment that we talked about before, notices, okay, it needs a dynamic loader, I'll load that for it, and then I'll just hand it off to the dynamic loader and walk away. And that's it. That's basically the begin. So where does our journey begin? It starts at this system call that is literally what gets called when you're at a terminal. If you're in a terminal and you do / your binary executable name, all the shell does is take the path there and pass it off to this XCVE system call. Does very little other than that. And that gets passed over to a dynamic loader from the kernel. That dynamic loader eventually calls _start, which eventually calls _libstart main, which eventually calls our main function. We finally figured out how we get to main, and then all of the fun actually begins. Okay, so what did we learn today? We've learned quite a bit. We've learned all the steps that it takes to get to our main function that we just went through. We learned how to make a small enough binary to easily inspect, because if we do a bigger binary, we're just going to be going through a whole lot more data, and it's all the same thing, it's just harder to work with. We've learned a little bit about the ELF file format. We've learned where our code is and what code is added for us on behalf of the compiler and the linker. We've learned about libc's _libc start main. We've learned about the start symbol. We've learned about the dynamic loader that loads our program, maps everything into memory, moves it around, patches our program for us so that it's correctly callable. And we've learned about the syscall XCVE, which allows us to actually invoke the kernel and then get into the dynamic loader. But what did we not learn today? Because there's a whole bunch. This was kind of just the introduction into actually how programs get executed on Linux. We didn't learn about the specifics of libc start main at all. It's more complex than I let on. We didn't learn anything about the exact layout and contents of ELF files, what's in the header, the difference between sections and segments, where things live, different string tables, and things like that. We didn't learn about the full responsibilities of the dynamic linker. We talked a little bit about relocations, for instance, but that's a talk in and of itself. We didn't learn how this works at all on other platforms. What about Windows? What about Mac OS? What about BSD? Lots of fun dynamic loading tricks we didn't talk about. So if you're interested in kind of, okay, how can this help me hack things and things like that, I suggest you look into LD preload. There are a couple of talks out there that I've seen given where people use LD preload to do fun things. I believe there was one by Jan Erik who ended up putting something in LD preload that kind of rewrote all of the libc functions in charge of printing and just caused everything to be uppercased and append exclamation points to it. So you can kind of hack binaries that way, which is really fun. So given all those things that we don't know about, I want to give you some resources to go, because this was really just an introduction. The first one I'll talk about is Matt Godbold's The Bits Between the Bits, which is kind of what got me into this stuff. This is a CPPCon talk that talks about how to get to main for a C++ executable. And that talk goes even deeper than I was able to go in today. So take a look at that one. Then, of course, faster than lines, making your own executable packer is probably kind of the best, I would say, Rust-specific introduction or really guide to learning about this stuff. You essentially create your own dynamic loader from scratch, which is really cool. Patrick Horgan's "How the Heck Do We Get to Main" is really great, and gave me a lot of this information. If you're into Windows, James McNellis's "Everything You Ever Wanted to Know About DLLs" is really fantastic. So you can kind of essentially learn the same thing, but from a Windows perspective. And then John Thagen's "Minimizing Rust Binary Size" is a great resource if you want to make the smallest possible Rust binary so that all of this is a little bit easier to work with. All right. And that's it. That's my talk. If there are any questions, be happy to answer them.